Now the next thing we're going to take a look at is how the electrode potential varies if I change concentration. Meaning concentrations in standard conditions are 1 mole per dm cube. And if you remember, we had done this particular cell before, the zinc and the copper cell, which resulted in a particular potential difference of 1.10 volts. But this was carried out under standard conditions, and under standard conditions the E of zinc was minus 0.76, if you remember, the E naught, while the E naught for copper was plus 0.34. Now these E naught values, these two, are measured under standard conditions, and if the conditions change, we are able to predict what happens to these values. So let's start off with the zinc idea first. Alright, so if I take a look at zinc, the zinc half cell. Now the zinc half cell's half equation is this particular one, and it is how much? The E naught is 0.76 volts. Now this is carried out under certain conditions where the concentration of zinc ions is 1 mole per dm cube. And the point is that if you change the concentration of zinc, the E value will also change, especially if you can understand that the E value represents the position of the equilibrium in some ways. So if I look at this particular case, what happens to this E value if I were to change this concentration? Now we can use Le-Chatelier's principle to come up with that. To qualitatively, what happens to the value? Does it become more negative or less negative? Then we can even calculate it. It's called the Nernst equation. And there's a formula for that helps us calculate the value for the new E. For example, I tell you that I want to set up a cell where the zinc's concentration is not 1 mole per dm cube, but 0.1 mole per dm cube. Now for that half cell, would that half cell's E naught be less negative or more negative than this? Meaning on the number scale, will it become more minus or less minus? Now, the idea is that I have lowered the concentration of zinc. So using Le-Chatelier's principle, we can predict qualitatively what happens. So if I lower the concentration of a substance, how does the equilibrium behave? So if I lower the zinc's concentration to make it 0.1, the equilibrium will shift to oppose that change. So if I lower the concentration, it wants to produce more ion. Okay. So this particular equilibrium will shift to the left. So meaning if I've decreased the amount of zinc by lowering the concentration, the equilibrium will want to move to make more. So it will move to the left. And this E is a measure of the forward reaction. So if something moves left, so when I do this, when Zn is less than 1, the equilibrium shifts left. Okay, shifts left, and the E naught, or the E, when it shifts left, becomes more negative. That's the idea. And you can even calculate that using a particular formula. Now the formula looks something like this, by the way. You can also use a formula to find the exact value to prove that this is right. It is that the new E is equal to the original E naught plus what? Plus a certain new things. Plus 0.059 over Z or Z. I'll tell you what Z is. Into basically the log to the base 10 of what? Collectively of two things. The ratio of the oxidized species over reduced species. Oxidized means higher oxidation state. Now I'll explain all of this stuff. Basically, this exists to find the new value for E for this equilibrium. Now in this case, remember, it's always the higher oxidizing agent, higher oxidation state is the oxidized species, and that's the reduced species. Or the higher oxidation state is the oxidizing agent, reducing agent. The oxidizing agent is the higher oxidized species. So basically what they're saying is here, we can use this and apply this to this. It means that the nu E, which is not standard, is equal to standard plus a few things. Now plus what? Plus 0.059 over Z. Now somebody's done the math for this. We don't care how this is derived. But here Z represents the number of electrons transferred in the equation. So if I'm doing it for this equation, E naught will be minus 0.76, and so far Z will be 2. And on the right hand side, the oxidized species is log of Zn2 plus's concentration. This is square brackets meaning concentration, and this is the concentration of the zinc metal. Now when you're given the concentration of a zinc metal, you'll take that to be 1 in this case, because there's no concentration of metal. That's the thing. So when I apply this to the top equation, let's do that. Okay, so they're saying you can find the nu E by taking the old E naught, which is minus 0.76. Okay, so I'll put that in white. E naught is minus 0.76 plus, this is a constant 0.059. Just take that. Now what will you divide by? The number of electrons. So if I go back on top, how many electrons are being exchanged? 2. It seems pretty straightforward, no? Doesn't it? So 2 times the log to the base 10 of the oxidized over reduced. The problem is the oxidized is now this only value, which is 0.1. Over, there is no reduced. Reduced is the metal. So for metals, we don't even write them. Just leave it as is. That's perfectly fine. Literally like this. So there's no need to write over. And this is all you have. So literally, this is what you have. So I'll just bring that right here. And I just solve for it. And you'll see it will be corresponding to what you had predicted. Remember what you had predicted. It'll shift left and become more negative. So this value will be more negative than minus 0.76. And you can find that out also. In this case, what is that? So let's do the math. 0.76 plus 0.059 over 2. 0.295 into the log of 0.1. What's the log of 0.1? Minus 1. So these two minus this. So basically minus 0.76 minus 0.0295. It comes out to 0.7895. And that's the new value, which by the way must realize is more negative than E naught, which is minus 0.76. So that's how you actually calculate. And this is what we just did, is called the Nernst equation. And it cannot just be applied to, a metal half cell. Could be applied to any half cell. And you'd get the answers. Yeah. Now we can also apply this to any equation where both the species can be changed. For example, if you remember, there was iron 3 plus and iron 2 plus. And its E naught was how much? Let's say plus 0.77 volts. And I'd say, okay, let's find the new E, let's find the new E when I said, let's take the concentration of Fe3 plus as 4 moles per dm cube, while Fe2 plus is only, let's say, 0.4 moles per dm cube, for the sake of our, And then what do we do? So the formula was what? It is the new E is the old E naught plus 0.059 over Z into log of, what we say, the log of the oxidized over reduced species over reduced species. Now oxidized is the higher oxidation state. So literally here, this is for iron, this is Fe3 plus, and this is Fe2 plus. And for iron, Z must be 1 because only one electron being exchanged in the equation. And you just plug in these values and this is plus 0.77. So what you do is E would be 0 plus 0.77 plus 0.059 over 1 into log of what over what? Log of 4 over 0.4. So you'll first divide, then log, then multiply, and then add. That's the chain by which you do this. So 4 over 0.4 is 10. Log of 10 is 1. I just took that, so it will give me 1. And there's 0.059 plus 0.77. And when you add them up, what do you get? This comes out to 0.829, which is clearly more positive than the original value. And here what I had done, I had increased this and decreased this. By increasing this and decreasing this, the equilibrium shifts right. Makes it more positive, and then mathematically, we've also proved it becomes more positive. Alright? Now this method comes in really handy for those half cells where the iron is not very soluble. Yeah, like silver bromide, silver chlorides, so lead salts chlorides. So this particular E will help us find out the E naught where maybe the concentration was pretty low, like 10 to the power of -4, -5 also. You can find the E for those cells also this way.